Hello everyone. Today I have the pleasure to present to you our work on difficulty of defending self-supervised learning against model extraction. My name is Adam Dziedzic, and this is joint work with Nikita Davan, Muhammad Ahmed Kalem, Jonas Guan, and Nicola Paper. In the supervised machine learning APIs, a user selects an enabled data point and sends this as a query to ML API. The API responds with low-dimensional outputs such as labels or softmax scores. In the self-supervised learning APIs, encoders transform complex queries into high-dimensional representations. The representations can be further used to train predictors for multiple downstream tasks. The representations reveal more information about the model behind the APIs than the low-dimensional outputs returned by supervised models. Behind the scenes, it's a costly venture to create the self-supervised learning APIs. First, it is hard to collect the large amount of data required to train the encoders. Then we also need to hire ML experts to tune parameters of the encoders. And finally, there's expensive hardware such as GPUs or DPUs required for training and inference of these encoders. For instance, it was reported that a single training run of the GPT-3 encoder costs north of $12 million. However, the querying part may be malicious. In our work, we find that attacks against SSL models are query efficient, and second, existing defenses against model extraction are inadequate in this SSL setting. The framework of our attacks is inspired by Siamese networks. We query the victim encoder and then use the outputs to train our copy of the encoder. We minimize the loss between representations obtained from the victim encoder and our stolen copy. And the loss functions play an important role in stealing encoders. The standard loss functions, such as MSE, are used to directly minimize distances between representations from the victim and the stolen copy. Modern batch contrastive losses, like inference or self-nearest neighbors, they compare not only positive but also negative pair samples. And we find that using the same contrastive loss functions for stealing encoders as well as for their training performs the best. Next, we present the performance of stealing a victim encoder pre-trained on the ImageNet. So the results represent the linear evaluation accuracy on many downstream tasks. The first row is for the victim encoder, the remaining rows are for stolen encoders. The performance of stolen encoders increases with more queries, and even with number of stealing queries being less than 1/5 of the number of victims' training points, we are able to extract encoders of high quality. Having discussed our attacks, we consider different defenses to protect encoders. There are many ways how to defend supervised models, for example, by poisoning the representations, using detection, or increasing the cost of queries. However, these defenses are not easily applicable to encoders. So let us focus on watermark defense. Here we embed the rotation task into encoders during training. As an example, the task is a binary classification where we have to classify if a given image is rotated between 0 and 180 degrees or between 180 and 360 degrees. As a result, the watermark encoder and its stolen copy perform well on this task, and they return correct rotation range. In the graph, we show the watermark success rate on the y-axis as a function of number of queries used for stealing on the x-axis. So we observe that for a legitimately trained model, the watermark success rate is roughly 50%. So this is almost random accuracy. On the other hand, for stolen encoders, the more queries are used for extraction, the higher the transfer rate of the watermark. And this also holds for many loss functions used for stealing. To conclude, we show that stolen encoders achieve high performance on many downstream tasks. The contrastive loss functions, such as inference, they perform the best for stealing encoders. And defending encoders against attacks is challenging, since representations reveal a lot of information, and also these defenses cannot be easily applied out of the box to protect encoders. And this requires us to design new defenses against encoder stealing. With that, I would like to thank you for your attention.